So this is D'Alembert's solution to the wave equation. So sections 12.32 and 12.33. We motivated D'Alembert's strategy last time, which involves using certain, natural variables. So just to remind you here, so something has changed in this formulation of the problem that I should point out immediately. So for D'Alembert's solution, we are considering a string that's infinitely long. And so for now, that seems unrealistic, but we will make things work out. So for now, you might be thinking, well, how, when do you ever encounter a string that's infinitely long? Well, in mathematics, we can artificially create an environment like that from a realistic situation, and actually have, right, if you think about it. And so more on that later. So for now, just go with it. So here we have an infinitely long string, and because it's infinitely long, there are no boundary conditions. So that part's very important to keep in mind. We just have initial conditions in this problem. Initial conditions, and of course, our new favorite PDE, the wave equation. So, just think of a really, really long string. So the idea behind D'Alembert's solution is to introduce these new variables. We have y equals x plus ct and z equals x minus ct. And so this was completely, this was motivated by the formal series solution of the wave equation using separation of variables, where we get a product of functions that are, one is a function of x and one is a function of t and c in there. So using identities, we can rewrite that series solution in a different form where these variables naturally pop out, x plus ct and x minus ct. So the idea here is to parameterize the solution with these new, more natural variables. And when we did that last time, what happens is we get a much simpler looking PDE. So last time we showed if you use this variable change, we get, I think the wave equation ends up looking something like, so that's a y, that's a z supposedly. And then I need to throw on a c squared, I think. So we ended up something like that. So that's a y. And then there should be a v right here. And so please see the lecture last time. Don't ruin your eyesight looking at what I just wrote there. So see last time, we're using this variable change, we were able to simplify the PDE drastically and rewrite the solution in this form. So, the language we introduced last time was, we referred to these as traveling waves, whereas the formal series solution of the wave equation using separation of variables results in a solution involving what we call standing waves. So here, these are D'Alembert's traveling waves. And so the idea now is to assume the solution that we're looking for, which represents the vertical position of the string at any, point in time t and point along the string x, that this is a combination of these traveling waves. So, and then, we'll do some mathematical techniques, for example, to plug it into the PDE to see what happens. But before we do that, there's one other little thing we have to do. So, and we need these functions to be twice differentiable because we have a PDE that's second order, and we're going to be taking, second partials via chain rule. And presumably, the only extra information we have in this PDE, the wave equation is just a PDE, but the information we use to really find the actual solution for this problem is the initial conditions. It's the information from, u of x and v of x the initial position of the string and the initial velocity of the string, if any. So here, here's one little sneaky math thing that we have to do. And, and this is a traditional approach to solving problems that we've used for a long time, which is to take the big, more complicated problem and try and break it down into multiple, smaller, easier to solve problems. Solve those problems individually, and then combine the solutions to find the solution of the original, more complicated problem. So here we can use the fact that the wave equation is a linear operator, and the set of functions that satisfies the PDE specifically forms a vector space. How did this 1 comma survive? Anyway. The plan here now is to separate the PDE into 2 different PDE problems with different initial conditions. So this is our kind of divide and conquer approach. Okay, so then we'll solve each separately and then combine the solutions. So assume U has the form U1 plus U2, not the band, where U1 satisfies this PDE right here. So it's still the wave equation up here. The main difference is in the initial conditions. So this initial condition is the same, but we've made the initial velocity for this PDE involving U sub 1 be trivial. And U sub 2, here, again, it's still, the wave equation, that's the same. Now, the initial position is made to be trivial, and we've got the initial velocity from the original problem. So essentially, what we've done is we've divided up the original initial conditions between these 2 problems. And now we're going to try and solve each of these PDE, posed on an infinite string individually using D'Alembert's traveling wave approach. So I just want to see us to see the big picture first before we actually start solving all these little equations, before we go down the little rabbit hole. Suppose we can solve these 2 PDE for U1 and U2. So then I claim the sum U1 plus U2 will satisfy the PDE and the initial conditions. So the PDE is satisfied purely because of the linearity. We take the time derivative of U, replace U with U1 plus U2, and now use the linearity. So this is, the thing that is in the background making stuff work. I can just distribute this derivative to each term. And now U1 satisfies the wave equation. So it equals C squared times, the second partial with respect to X. And similarly, U2 satisfies the wave equation. So this second partial with respect to T equals C squared times the second partial with respect to X. And then now, once again, use the linearity. Again, the linearity, we can pull the derivative out. We can pull the derivative out. We can pull that constant C squared out. That's linearity. And so now I have this equals C squared plus the sum of the functions U1 and U2. But, U1 and the sum of the functions U1 and U2 just gives us back our original function, U. So if you look at the left end here and to the right end, we see that our function U, that is the sum of U1 and U2, that satisfies the heat equation. So check, PDE is satisfied. And well, what about initial conditions? And so here, if we look at U of X0, remember U is U1 plus U2, and I replaced the T with 0. And so now U1 by construction satisfies capital is equal to ux. That is the initial condition for u1. And here's where, you know, the strategic decomposing of the initial conditions between these two PDE pays off. The initial condition for u2 by design is 0. And so here u plus 0 gives us capital U here. And so our original function u satisfies the original initial condition of the original PDE. And we can also check the initial velocity requirement is satisfied. Once again, linearity to the rescue. The partial derivative of the sum is the sum of the partial derivatives. U1 by construction, its initial velocity is 0. U2 by, you know, construction, its initial velocity is capital V. 0 plus V is V. The end result here is our function U, our function U, that's the sum of U1 and U2. That satisfies the original initial condition. And so here, you know, you see the original initial conditions are satisfied, as well as the original wave equation PDE. This, if we can find the solutions U1 and U2, then you know, by adding them, we can find a solution to the original PDE. And then we have to move on to the real task of finding this infinitely long string, right, everybody? Yay. Okay, so let's now solve this system of PDEs here for U1. And we will solve this problem using D'Alembert's traveling wave strategy. So I'm going to assume U1 equals F sub 1 x minus CT plus G sub 1 x minus CT. We will make this same assumption for U sub 2. And if you add those two, you can get F1 x minus CT plus F2 x minus CT and make it look like the original formulation of what we thought the solution U looked like. Some of these two traveling waves, one that moves to the right and one that moves to the left. Think of your Calc 1 graph translations and keep in mind T is time. So here we assume it's greater than 0 and C is a positive constant. It's a speed. So think of your graph translations. One moves to the right, one moves to the left. Okay, so for to start with, what I first want to do is take advantage, get all of the information I can from the initial condition that's trivial, that's setting something equal to 0. So that's a simple equation. Let's first use that to try and get information about the system. So now we're looking at U1 and we're going to take a partial with respect to T. The partial of U1 with respect to T, so you've got F1 here. It would, you know, we'd need to do a chain rule. So we do the derivative of the outside would be F1 prime times the derivative of the inside. And here the inside is x minus CT, and we're doing a derivative with respect to T. So the derivative of x minus CT with respect to T is minus C. So we end up getting this equation here. So that's F prime, the derivative of the outside, times minus C is the derivative of the inside, which is x minus CT derivative with respect to T, plus, and so now we do the same thing with the second term here. So now plus, so this is that plus symbol. Again, if you look at this function G1, I'm going to do a chain rule for a T derivative. The derivative of the outside will be G1 prime x plus CT times the derivative of x plus CT with respect to T is just C. And that's exactly what we have down here. So if we take a look, this is the derivative of this term right here using a chain rule. derivative of the outside times derivative of the inside. And we're told that, if you plug in a 0 for t, then the left-hand side of the equation is 0. And so that's what I've done here. I plug in a 0 for t. The x minus ct, when you plug in a 0 for t, just becomes an x. The minus c we just copy down. That was from the chain rule, the derivative of the inside part. And similarly for the other term here, the x plus ct, replace the t with 0. I just have an x, and then here's the c from the chain rule. And we're setting it equal to 0. So I'm going to take this negative, I'm going to take, what am I going to do? Yeah, I'm going to take this negative term right here, move it to the other side. So we get g1 prime of x times c equals f1 prime x times c, and we can cancel the c's. So when I move this term over, we get a c on both sides. So then c is greater than 0. Cancel, cancel. We conclude f1 prime of x equals g1 prime of x. So we now integrate both sides. So now integrate with respect to x. That's supposed to be a d. So we get f1 equals g1 plus some constant, which I'm calling k because we're using c already. If you differentiate both sides of this equation, you get back to f1 prime equals g1 prime. So now let's use the other initial condition. So this is the non-trivial initial condition, which is the initial position. So again, be careful here. We're going to go back to this. Replace the t with 0. So the t here, this t right here, t right here. Replace it with 0. We get f1 plus g1. On the other side, we're given that it equals to capital U of x. We know we're given the initial position of this string. And so now I replace f1. So here, f1 we said is equal to g1 plus k. So go there and then go over here. And this f1's been replaced. So now g1 plus g1, I have 2g1 plus k. So now look, this is progress. I have 2g1 plus k equals u of x. So now let's solve for g1. If we can find g1, then we also know f1. Once we know f1 and g1, we've solved the whole problem, because we have all the parts. So move the k over, move this k over, divide by 2. I get g1 equals capital U minus k divided by 2, and I've split it up into 2 fractions. So there's g1. Now I can plug it right into here and find F1. F1 is G1 plus K. G1 is, the initial position divided by 2 minus K over 2. And then I'm doing minus K over 2 plus K, so 2K over 2 minus K over 2 gives me K over 2. So here is F1 and here is G1. And so now we can combine them and find our solution to the original, problem here. So we get, when you add them, so when I add this function, and you replace the x's accordingly, so there I'd replace it with a x plus ct, and I'm adding it to this function, replace the x with a x minus ct. These terms, the k over 2 terms, they cancel. Cancel. We just have this term here with the x replaced with, oops, that was wrong. We have this term here with the x replaced with x plus ct, and this term here with the x replaced with x minus ct. So we found U1, and now we shall basically follow exactly the same procedure to find U2. Evan.
I just had a question real quick. So in the derivations we did above, we assumed that the time variable was 0, and then we just used the initial conditions at that point. But in this last step, we seem to plug in the time variable again. What allows us to do that?
So could you ask that question again? I don't quite follow.
Oh, I'm sorry. So in the other steps, we just have it these f and g as functions of x, right? We assume that the time component is 0, so we can use our initial conditions. But in this last step right here, we assume that the time variable is non-zero again. So how are we allowed to do that exactly?
I'm just replacing this squiggle right here with this squiggle.
Okay, so those are different x's then, like we're interpreting them differently.
Well, they're the same. I mean,
okay.
It's it's the input of the function.
Okay.
So here when I make t equal to 0, this part just disappears. And you just get f1 of x. So that's what this is, just with the t made 0. And so now the t is not 0 anymore.
But what we're doing is we're showing that that these are equal at time t equals 0, but then how does it follow that they're equal for times for t not equal to 0? So I'm not quite following.
So here, all I need to do is find f1, the function f1, and then stick this squiggle inside f1.
Okay.
And so here I found the function f1. You can call this x or smiley face or whatever variable you want. Now I know the function f. Now I'm going to stick this squiggle in here.
Okay, so we're not treating f and g as multivariable functions. We're treating
They're not
this
multivariable functions.
Okay. Got
They're
it.
not. Yeah, that's the thing.
Okay.
This is a composition, right? That's f1 composed with x minus ct. That's why we only require f and g to be differentiable. We don't say they need to have partial derivatives because they're univariate functions.
So then we're assuming that our U1 and U2 are multivariable functions that can be written as sums of single variable functions in a sense.
Well, once you do the composition, this is now a multivariate. This is a new multivariate function. This is now a new function, whatever you want to call it. Okay. Z of CT. once you do the composition. So this is the composition of a univariate function, and x minus ct is a multivariate function. X minus ct is parameterized by x and t. And so once you do the composition, then that composed function is now a function of c and t. But the underlying function f1, this is just a function of one single variable, you know, call it z or whatever. And now z happens to be a function of these two variables, x and t. And I can't remember if y is x minus ct or z is x minus ct or whatever, but that's what's going on. One of them is a function of z and the other one is a function of y, but z and y themselves are functions of x and t. And so this derivative here is just a regular derivative. This is just a regular Calc 1 derivative. And then here we're doing a partial. So here there's some partial trickery happening here.
Okay,
But,
got it.
yeah. Thank you for that question. Does that make sense? Yeah, there's a lot of kind of machinery in the background. And so this is a fundamental difference in, like, you know, the traveling wave kind of, that we start with this function f that's a function of this single quote unquote natural variable. And I can't remember now if z equals x minus ct or if z equals x plus ct. So, you know, this might be wrong, but you get what I'm trying to say. So it's all a really kind of a function of those natural variables, and those natural variables themselves, we can parameterize with our original x and t variable. And so we're kind of chasing it that way. So we're now going to solve for, so let me just do a quick geometric interpretation here, I guess, before we just dive into the math. So for U1 here, we've written it this way. And if you just think about your Calc 1 or pre-calculus graph translations, it's the same graph in both cases, just one's being translated one way and the other's being translated the other way, So here, remember, CT is positive, so x minus CT will be a right translation, and x plus CT will be a left translation. And so here, what we're saying is, the minute at time t equal to 0, you have your initial position of the string u of x, okay? The minute time starts, what happens is, the string, the shape of the string basically breaks into two, where the shape is identical to the initial shape, but the amplitude is half, and one of them is moving to the right and one of them is moving to the left. And it sort of sounds crazy, but I've thought a lot about this, oddly enough. And if you think about a really long string. So let's take a really long string and just pinch it up at the center. Okay, so there's my really long string. I've pinched it up at the center. Let me throw on some kind of horizontal reference here. Okay, now look what happens if you let the long string go. So you've pinched it at the top, you let it go, this part goes down. The string, this middle part of the string has gone down, and you'll see it does kind of have two waves emanate from that center position when you let the string go. You know, if you just think about it, a very long string, pinch it up in the center and let it go, that center point will drop down. What happens is you get two waves that start to emanate from the center and move out to the left and the right, and they sort of take on this triangular shape. So this is basically claiming that, you know, mathematically, that's what we're showing is happening. So here, if starting at rest, the initial position of the string will break into, the string won't break, but the actual waveform will separate into two halves, one moving to the left and one moving to the right at equal speed, but with half the amplitude of the original. So, you know, our U1 solution we're saying is a sum of these two waves. So there's my initial position that I just made up and made it look weird to be counterintuitive. And now when you start time, let the string go, what happens is you get this left moving wave and right moving wave with exactly the same shape as the original, but half the amplitude. To me, it's a little more intuitive when I do my very simple experiment where you take a string and pinch it up at the center. Let that center point go. You kind of, expect to see these sort of two emanating waves from the center moving out. Evan.
Sorry, I just had another question. So when we say that the waves are moving left and right, this is with respect to X, the spatial variable, right?
Yeah.
So what does it mean to say a wave is moving without respect to the time variable? Because I thought we were assuming that the individual points on the wave aren't moving.
So this is when, this is when t equals 0. And this is when t equals 1. So on and so forth. So now when you say t equals 1, this is no longer a variable. Now it's just a function of X, and we're graphing that, input versus output.
Okay, but the points on the wave themselves aren't actually moving, just the wave shape is moving along the string.
Well, I mean, this point here moved up. It was originally flat, but now it's bumped up.
Okay, but no horizontal movement. Right?
No. So, part of it's an infinite string. So yeah, you tell me. The ends aren't tied down. What does horizontal mean when it's an infinite string? You might have to send D'Alembert an email on that one. Yeah, I don't know about that. It's an infinite string, so horizontal movement doesn't make sense, right? It's like the string is literally the real line to some extent. I mean, it's that long. So yeah, So let's solve U2. Here we have the trivial, shape with some given initial velocity. Make the same traveling wave assumption a la D'Alembert. And strategically first use the trivial boundary condition. It's the simpler condition. Setting things equal to 0 is nice. We can move stuff over and maybe figure out stuff is equal. So as before, in this equation, we replace t with 0. And so, the minus ct part goes away. And then set the whole thing equal to 0. And then I set this whole thing equal to 0. And so I did that over here. With the t equal to 0, the ct part goes away. So now I have 0 equals f2x plus g2x. And so then I moved the g2 over, so I get f2 equals negative g2x. So if I can find one of the functions, I can find the other. So now what we want to do is to use the other boundary condition. I want to use this boundary condition involving a derivative. Okay, so eventually I'm going to have to take the derivative here. So note that if f2 equals negative g2, then f2 prime equals negative g2 prime. We'll use that in a second. So now I want to take the t partial of u. And so go back to this equation right here. I want to take the t partial of this function, replace the t with a u, with a 0, replace the t with a 0, and then set the whole thing equal to v of x, the initial velocity. So here we go. When you take the derivative, we need a chain rule here because we're doing a t derivative. So I'm taking the t derivative of this. And so this is where what Evan said, comes into play here. F sub 2 is a univariate function. So I do f2 prime, derivative of the outside evaluated at the inside times the derivative of the inside with respect to t. The inside is a multivariate function. Here, x minus ct partial t gives me a minus c. And so this expression is, exactly what you see right down here. That's with chain rule, and then replace t with 0. So then when you replace t with 0, this term disappears. So we have f2 prime x times negative c. And with the g term, it's the same thing. Again, g is a univariate function. So we do derivative of the outside, g2 prime, and then derivative of the inside, that's where the c is coming from. And then finally, let t equal 0.
All right, yeah.
Finally, let t equal 0. So, and then I use our assumption of equality. I know f2 prime equals negative g2 prime. Okay. So, all righty, here we go. So now we can solve for stuff because we've eliminated, one of the functions. We have an equation here. So think about it now. Here, if we add the two minuses cancel, and we get, all right, if someone's mic is unmuted, please unmute it. So we get 2cg2 prime. And so I have vx on one side, 2c2g2 prime on the other side to solve for g2 prime of x. So we get g2 prime of x equals v of x over 2c. And so, we should think about this in a calc 1 way. What we're saying is that g2 prime then is an antiderivative. So if we want to find g, I need to find any function whose derivative, when you take the derivative of this function, you get back vx over 2c. So I'm looking for any function g of x such that when you take its derivative, when I do a, derivative with respect to x, I get back this function. So we know using the fundamental theorem of calculus, we can actually manufacture a function. Oops, sorry. We can actually manufacture such a function. So, all right, folks, this is the part where you have to remember your calc 1. And I don't know if, I don't think I put this in the review. Maybe I should. So this is fundamental theorem of calculus going way back. First of all, I changed the variable of integration to s. Be careful. Remember, the variable of integration is what's known as a dummy variable. It's not really there. It's just a placeholder. Here, the actual variable is right up here in the bound. There's your variable. And, think all the way back to calc 1. This is a special way of defining a function of x. It's an integral form. And the fundamental theorem tells us that if you try to take the derivative of this function, if I want to do a derivative with respect to x, so here, the derivative of the integral, what happens is that the derivative and the integral cancel out. We just end up taking the x and plugging it in. And so fundamental theorem of calculus part 1 says if you define g of 2 of x to be this integral from some constant a to x, the function v over 2c, the fundamental theorem of calculus will tell us, that the derivative of that will be what we want. It'll be the velocity divided by 2c. So we're going to define g2 of x to be this integral, where if we know the initial velocity, we can find g2 of x. And once we know g2 of x, we can use the fact that F2 equals negative G2 to find an expression for F. And so now we know F and G, we can create U2. So now I'm replacing the X with X minus CT and the X with X plus CT and, F2 and G2 respectively. And we get, and then here I flip the integral around to get rid of this minus sign. So to get rid of this minus sign, I flip the integral around. So that's what you see over here. And here now, using properties of integrals, we can combine these two integrals into a single integral. And so now I have an expression here for U2. So what we can do now in theory is take U1 and U2 and put those together. So now back to the original problem in terms of the U variable. Remember, we said let U equal U1 plus U2. That was how we started this. And then we solve for U1 and U2 separately. U1 is this function here that uses the initial position. And U2 is this integral here that's integrating the velocity. So that's good. That makes sense with the units, right? Because you're integrating the velocity and adding it to the position. And so it's important to just take a second, take a beat here, and think about what we've done, because this is going to blow your mind. We solved a PDE without using separation of variables. For this, there's no separation of variables. Separation of variables was not used for this. This was done without separation of variables. No variables were separated in the solving of this PDE. So what does that mean to you? Well, if you're given a wave equation on this infinite string, you can immediately jump to this closed form solution. This is the answer. There's no worrying about convergence. There's no doing anything. That's just a formula for the answer. So if you see an infinite string problem on the homework, you can just jump right to the answer. You don't have to rederive the entirety of D'Alembert's solution as we have just done. Of course, you should review it, make sure the math makes sense to you, but we're never going to redo that process ever again. When we have an infinite string, we're just going to jump right to this solution here because we've showed that it formally is the solution. We still have to verify that it satisfies the PDE. That's still something we have to do, and we still have to check the initial conditions. So I'll check the initial conditions here, and I'll let you verify that it satisfies the PDE. So here, I claim that this function will satisfy the wave equation, and I'll leave it to the interested reader to verify. Who am I kidding? It's on the homework. And let's show the initial conditions are satisfied. If we let t equals 0, then this becomes an integral from x to x. So think about what happens here. If you let t equals 0, this becomes an integral from x to x. So that's just 0. And the minus ct part disappears. So I get 1/2 u of x plus 1/2 u of x, which is u of x. Perfect initial position requirement is satisfied. And if you take the derivative and let t equal to 0, when we take the derivative, I do derivative of the outside times derivative of the inside with respect to t. Derivative of the outside times derivative of the inside with respect to t. Let the t part equal 0. You get these two functions are negatives of each other, so they get canceled out. Over here, when you take the derivative using fundamental theorem of calculus, you can break this up and show that the v, all these integrands work out this way. Okay, it's just using fundamental theorem of calculus, but you first have to break up this integral. So to use fundamental theorem of calculus, I need to go back to this original form. So I'm going to go back a couple of slides. So to take the derivative of v, it should first be written in this form. So here, I'm going to take this back to this form and then take the derivative of each of these individually with respect to t. Where's it x? Yeah, t. So I'll let you work that out. So now, is it time? Oh, so I did a quick example here. So just for a technical point, you know, this integral now, like let's assume the bottom bound is a constant just for simplicity here when you split up the integral. Just a technical point to go back to what Evan was talking about. The integral itself is a function of one variable. But when we replace the upper bound with x plus ct, x plus ct, you know, you should think of that. That's really a function of two variables. So here, when you take the derivative of the integral, you're again doing a chain rule. There's a derivative of the outside, and you take that and plug it into the function times the derivative of the inside. And so with respect to t, so that's where this is coming from. And then you replace the t's with 0. So anyway, I'll let you think about, it's a little bit of like Calc 1 chain rule, Calc 3 stuff, you know. So here I did this PDE, you know, it's just kind of a random toy problem where I had, I don't know why, I had the initial position be 0 and we gave it some initial velocity that satisfied this profile here. And so now the whole point is, once I've identified this as a wave equation on the infinite string, I'm not doing anything other than just going right to the formula. I just need to figure out what's capital U, in this case, capital U is 0, and what's capital V, in this case, it's given to be 2 over 1 plus x squared, and then I can just go to D'Alembert's formula and calculate the formula. And now we're just doing, you know, an integral. So here U is 0, so nothing to worry about there. And the integral here, if you go back to Calc 1, turns out to be arctan. And the 2's cancel. And so that's my solution. And we're done to the PDE. It's not a series solution. You know, it's a closed form solution and there's no convergence issue. I mean, in theory, we still need to verify that it satisfies the PDE and all that kind of stuff, but you know, it'll work out. That's why we're talking about it. And here we can talk about what happens as t goes to infinity, you know, whereas for this particular PDE, there turns out to be a limiting behavior. I don't know if you remember the graph of arctan, but it has pi over 2 and minus pi over 2 as horizontal asymptotes. And here, when t goes to infinity, the whole thing goes to plus infinity. And here, when t goes to infinity, the whole thing goes to negative infinity. So you get pi over 2 minus pi over 2. So we can show that there is a limiting, I don't know what, shape to this solution. So again, I don't know what the physical meaning is. That part, you know, we're going to have to think about. So here I did some quick graphs for you. So here is the shape at time t equal to 1. So I don't know if this is realistic or not. I assume c is 1. This is the graph when t equals 1. And here I also graphed the underlying, there's a right moving and left moving underlying waves. And then I advanced time. So now you can just look at what happens to the whole thing as time moves forward. You can see these waves are pushing out, you know. And so those are our so-called traveling wave phenomenon here. Explaining, so the dark curve is the string. So this is the string, and this is at time t equal to 1. At t equal to 0, it's a horizontal line at t equal to 0. T equal to 0. What are you doing to me? At T equal to 0, we just have the horizontal line, then, so yeah, I'll let you take a look at this. Think about D'Alembert's solution. It's a totally different type of solution. It's not a series solution, but, and there is a way to extend it, to use D'Alembert's solution to solve the wave equation on a finite interval. Okay, it's called using a technique known as the method of images, and it involves using periodic extensions, something we've already talked about. We can take a finite string, periodically extend it so that it's an infinite string, and then try and use D'Alembert's solution to solve it. Okay, so that'll come up sooner than you think. So here, I'm going to stop right now. I want to thank you all for your time.